A flow meter is a device that measures the rate or quantity, volume or mass of a liquid, gas, or vapor moving through a pipe or channel, working by using different physical principles like pressure changes, velocity, or electromagnetic forces to calculate the flow, with specific mechanisms varying by type. For example, ultrasonic, magnetic, turbine, to provide data for process control, billing, or monitoring. The fundamental types of flow meters are categorized by what they measure, volume or mass, and their operating principle, including volumetric, positive displacement, turbine, vortex, ultrasonic, magnetic, for volume, and mass flow, Coriolis, thermal, for direct mass measurement, plus differential pressure, orifice, venturi and velocity, paddle wheel, types, all designed for different fluids, conditions, and accuracy needs in industrial applications. How flow meters work. General principles. While specific mechanisms differ, flow meters generally rely on these core ideas: measuring resistance, restriction. A constriction, like a venturi or orifice plate, creates a pressure drop, and the flow rate is calculated from this pressure difference. Volume type flow meter. 1. Magnetic, mag meters. A magnetic field is applied, and the voltage generated by the conductive fluid moving through it is measured. In an electromagnetic flow meter, the magnetic field is generated by a set of coils. As the conductive liquid, like water, passes through the electromagnetic field, an electric voltage is induced in the liquid, which is directly proportional to its velocity. This induced voltage is perpendicular to both the liquid flow direction and the electromagnetic field direction. The voltage sensed by the electrodes is further processed by the transmitter to give standardized output signal or displayed in appropriate engineering unit. Electromagnetic flow meters are based on Faraday's law of electromagnetic induction. Formula: E equals K times B times V times D, where E is induced voltage, K is flow tube constant, B is magnetic field strength, D is electrode spacing, and V is mean flow velocity. The flux density of the electromagnetic field in a given flow meter and the distance between the electrodes are constant. Therefore, the induced voltage is only a function of liquid velocity. The induced voltage is not affected by the physical properties of liquids like temperature, viscosity, pressure, density, and conductivity, as long as the conductivity of the measured liquid is above the minimum threshold level. For reliable measurement, the pipe must be completely full of liquid. The electromagnetic field coil assembly is excited by pulsed DC technique, which eliminates the interfering noise and provides automatic zero correction. 2. Ultrasonic flow meter. Working principle. Ultrasonic sound waves are sent through the fluid, and the time difference between upstream and downstream signals reveals flow velocity. The transit time flow meter utilizes two transducers that function as both ultrasonic transmitters and receivers. The transducers are clamped on the outside of a closed pipe or inserted in the pipeline by using an isolating ball valve assembly at a specific distance from each other. Transit time flow meters measure the time it takes for an ultrasonic signal transmitted from one sensor to cross a pipe and be received by a second sensor. Upstream and downstream time measurements are compared. With no flow, the transit time would be equal in both directions. Ultrasonic. Sound waves are sent through the fluid, and the time difference between upstream and downstream signals reveals flow velocity. Formula: V equals K times D times delta, where V is liquid velocity, K is flow tube constant, D is distance between two transducers, and delta T is difference in time of flight. With flow, sound will travel faster in the direction of the flow and slower against the flow. The induced voltage is not affected by the physical properties of liquids like temperature, viscosity, press, density, and conductivity. As long as the conductivity of the measured liquid is above the minimum threshold level. For reliable measurement, the pipe must be completely full of liquid. The electromagnetic field coil assembly is excited by pulsed DC technique, which eliminates the interfering noise and provides automatic zero correction. 3. Turbine flow meters. Turbine flow meters are precision instruments used to measure the volumetric flow rate of liquids and gases, relying on the mechanical action of fluid, striking a multi-bladed rotor. Working principle. Turbine flow meters operate on a simple yet effective principle. As fluid flows through the meter, it strikes a multi-bladed rotor. The speed of the rotor's rotation is directly proportional to the fluid velocity. This rotation generates electrical pulses through sensors, which are then converted into a readable flow rate. 4. Vortex flow meter. A vortex flow meter has the following components: a flow sensor, operable to sense pressure variations due to vortex, shedding of a fluid in a passage, and to sensor operable. Convert the pressure variations to a flow sensor signal in the form of an electrical signal, and a signal processor operable to receive the flow sensor signal and to generate an output signal corresponding to the pressure variations due to vortex shedding of the fluid in the passage. The vortex flow meter is a broad-spectrum flow meter which can be used for metering, measurement, and control of most steam, gas, and liquid flow for a unique medium versatility, high stability, and high reliability, with no moving parts, simple structure, and low failure rate. The vortex flow meter is relatively economical because of its simple flow, measurement system, and ease of maintenance. It is widely used in heavy industrial applications, power facilities, and energy industries, particularly in steam processes. Mass-type flow meter. 1. Coriolis flow meter. A Coriolis meter is based on the principles of motion mechanics. When the process fluid enters the sensor, it is split during operation. A drive coil stimulates the tubes to oscillate in opposition at the natural resonant frequency. As the tubes oscillate, the voltage generated from each pickoff creates a sine wave. This indicates the motion of one tube relative to the other. The time delay between the two sine waves is called delta t, which is directly proportional to the mass flow rate. In a Coriolis meter, this principle is ingeniously scaled down and applied within an oscillating tube system. Instead of a continuously rotating planet, the meter's flow tube, or tubes, is electromagnetically actuated to vibrate, typically at its natural resonant frequency. This rapid, controlled oscillation creates the moving frame of reference. The fluid passing through the tube is the mass in motion. As this mass is forced to conform to the tube's vibration, it experiences the Coriolis effect, resulting in a measurable force that is the basis of the flow measurement. 2. Thermal mass flow meters. Heat is added to the stream, and the energy needed to maintain a constant temperature, or the resulting temperature change, indicates mass flow. Thermal mass flow meters operate based on the thermal dispersion principle. When a gas flows over a heated element, it absorbs heat from that element. The rate at which heat is absorbed is directly related to the mass flow rate of the gas. As the flow rate increases, more heat is carried away from the heater, leading to a measurable temperature change. 3. Orifice and Venturi flow meter. Orifice and Venturi flow meters are differential pressure devices that measure fluid flow by creating a constriction, forcing fluid to speed up and pressure to drop. The Venturi meter uses gradual contraction, leading to less head loss, higher accuracy, and higher cost, making it ideal for long-term use, while the orifice meter uses a sharp-edged plate, causing greater head loss but lower initial cost, making it better for budget-conscious applications with easy plate changes for different flow rates, although with lower precision and downstream pressure recovery issues. Both work on Bernoulli's principle, but Venturi offers better performance for critical applications, whereas orifice plates are simpler and cheaper for less critical ones. Orifice flow meter mechanism. A thin plate with a sharp-edged hole, orifice, restricts flow, causing a significant pressure drop. Venturi flow meter mechanism. A smooth, gradual narrowing, throat, followed by a gradual expansion, converting pressure to kinetic energy with minimal loss. Applications: water, wastewater management, oil, and gas chemical processing, HVAC, and utilities, food and beverage.